Hello friends, in today's class we are going to talk about different states of the process and we are going to draw process state transition diagram. Welcome here and we are talking about different states a process can have and we have already seen in the last lecture that process can be created and it can be destroyed or it can be terminated, right? So we have already seen these two states and we have seen the command related with this. One of the command was fork and one of the termination is, you can say, exit. Okay, now so with that we have a few things in our mind that a process being created, then it will be in a new state. Process execution, when process is allocated CPU and it is in execution, that is basically a process, then it will be in a state that is called running state. And if a process is waiting for an event to occur, okay, event, and what can be this event we will talk about shortly. So when a process is expecting some event to be occur, then in that case it will be in the waiting state, and finally if the process finished its execution, then it will be in the terminated state. Okay, so these are the four different state a process can be in: new, running, waiting, and terminated. Now uniprogramming, okay, where a system is running a single program. Okay, a single program is running. So in that case, what will happen in this case is that a process can be in a different state, uniprogramming environment, where we want to run a single program at a time, and we'll finish it off. Then we'll finish that program, and then new program will be selected. Now let's talk about a bit of event that that process might be waiting. Okay, so now there will be a process, any process execution have a is executed in this way. There is a CPU time required, then process goes for input and output, may require input from the user, or it may require to produce some output, and then again it will go with this some calculation CPU time, and again it will go for input and output. So this is the cycle, this is the cycle a process follows. Okay, so the event that I said that what exactly is the event part, right? I said that event part will describe what is the event that it may be waiting for. So event is something that it is waiting for one of the event. Major event is your input output operation, something expected from the user or producing in the output terminal. So in uniprogram environment we have this state that a process is created in the new state, then process in the run state, and then it get blocked. Why it get blocked? Because it is waiting for some event to occur, and in this case it is an input output event, and finally again it will be in the running state. This process will be repeated, and finally it will go and complete its task, and it will be in the terminating state. Okay, so that is a uniprogramming environment. What is the disadvantage of the uniprogramming environment? You can understand in this way, that if process is in the block state, then in that case CPU remain idle. Okay, it will not do anything, no execution. Okay, so that is somehow what we are doing. We are not utilizing, not efficiency, or it's a not utilizing no, not utilizing utilizing the CPU efficiently, right? So undesirable situation, we want an efficient utilization of the CPU. In that case, what required in this case is whenever a process goes for the block state, immediately we pick up what? We pick a new process, right? We have to schedule a new process so that it will go in the execution. And once it get blocked, and whenever this process will get ready, and then finally we'll pick it up. And that is basically a multi-programming environment where we are running multiple processes at a time. So what is the idea here? That once a process get blocked, or it is waiting for some event to occur, what we can do, we can pick new process and allocate it, right? So that is the environment we are talking about. And right now we are introducing a new term, that is a non-preemptive. Okay, so non-preemptive means we cannot preempt an execution. Okay, if a program requires CPU time, then it will be allocated as much time as required. Right, so we will not do any preemption of it. Okay, so that is a non-preemptive process, and if it itself get blocked because of this waiting, then it is okay. Otherwise we will not forcibly take the process out of the CPU. Okay, so that is your multi-programming or non-preemptive environment, and your process state transition diagram will look like this. So there is a new process, okay, and the moment it will be created, then it will be in ready state. Ready state means it is ready for the execution, and this ready state will be maintained in something like a queue in main memory, right? So we have now multiple process, and the multiple process are ready to run, and it will be present in a queue. That queue we will talk about, but it will be in the main memory, and it is ready for the execution. Then we will do the dispatching, and then it will be in the running state. So this process will be keep on running as long as it is required, and then if there is an IO event, then it will go to the state block or the waiting state, waiting for an event to occur. The moment this IO completion event occurs, then it will again go back to the ready state. Okay, so now this is a multi-programming environment where we don't have a multiple program, we don't have a single program, we have a multiple program. You can compare this diagram with this diagram, where when it is blocked, then only when it will resume, then again it will be in the running state. Okay, so there will be no ready state in this particular case. Finally, after completion, it will be terminated. Okay, so now here we have better utilization, we can say, of CPU. Better utilization of CPU. This is a new term here in this case, is dispatch and dispatcher. And right now you can have formal definition will come later, but now you can think of dispatcher as nothing but that allocate a process to a CPU, right? CPU allocation, it will take the process in some criteria, using some criteria from the ready state or from the job pool or from the queue, and it will allocate it to the CPU, and that is basically the task dispatch, and it is done by dispatcher. Formal definition I'll come later. Okay, now preemptive system, right? The next one is, we have already seen the non-preemptive system. Now what is exactly a preemptive system? Now, as we all know that operating system is interrupt driven, and that external event can also trigger a system call unusual situation, attention. Okay, so external event can occur anytime, and it will be in the form of, external event will be in the form of interrupt. And I told you that what exactly happen when interrupt occurs, right? So interrupt occur, what we do is during the interrupt we complete the current instruction. This is a repetition, complete the current instruction and save address of next instruction, right? So in that case, and if an external event occur, then we will service ISR will execute. We'll find the ISR. There are many issues involved in finding the ISR vectored and all. Vectored, and then there is one more is called polling. We'll complete that ISR and again we'll resume that execution. So preemption is nothing but forcibly taking because of an external event. So we will force a process execution, force a process to suspend, not terminate, suspend execution because of this external event. An external event can happen anything, and that we will see in the later in the course. Now with this is the exact process transition diagram that we are having, that there is a new process is admitted and go to a state that is called the ready state. It's a job pool, it's an area in the memory that is consists of different processes. Then it will go to the running state, then it will be keep on running utilizing the CPU until two things happens. One is your IO or any event wait. Some file is required to open or some file is not available, required to bring it from the disk. It will be in the waiting stage. And then upon completion or IO or event completion, again it will be in the ready state. So there is nothing new. This is same as your non-preemption system. The only new thing is, here in this case, is running process can be directly go to the ready state if an external event occur, and that event in this case is an interrupt event, right? So upon interrupt, we will save the process and the state will again go back to the ready state. And once it will be completed, it will be available in that job pool, or let's say in the queue, and again it will be selected by the scheduled dispatcher and it will be assigned for the running. Finally, upon termination, it will go and in the terminating state. Okay, so that is your non-preempt. It's a preemptive system where we can preempt a running program and it will go to the ready state. Now if the main memory space is not enough, okay, if that is the criteria, that what we are putting here, everything we are putting in the main memory, right? Main memory. So there is a waiting time, right? There is a waiting time, and all of them are available in where? In the main memory. Now think of a situation if the main memory space is not adequate or not enough, right? In that case, we have to utilize what? We have to utilize the disk. We have to put the process temporarily in the disk. That waiting can occur for an IO event, or it can be also in the suspension state from the ready state also, right? We are forcibly taking out some processes out of the memory, out of the main memory, because there is no enough spaces available, right? So that is another dimension into this process state transition diagram. Though this has not been stressed much in the examination, but still this is the process state transition diagram with a space allocated also in the disk if the main memory space is not enough. Okay, if the main memory space is not enough, right? So that is your state transition diagram. So we have a new, then ready, and then dispatch, and then timeout, and in that case Timeout is a new term. I'll explain you later. But so think over it that if there is an interrupt, that is the right word right now, correct term here right now. And event wait, that is your IO, that is in the block state. Event occur, then it will be in the ready state. Now from the block state also you can suspend. Okay, block state is where in the main memory, right? It will be suspend and it will be allocated where? It will be allocated to a secondary memory. And it will be in the suspended blocked state, and this suspended blocked state is in the secondary storage, right? Because not enough space is available. The moment right, and come to this ready part, and here also a process can be picked and put into the suspended state, and it will be in the disk and it will be in the suspend ready. It is ready for the execution. If the space available, then again we can pick the process from the suspend ready and we can activate it to a ready state. In the suspension state where it is suspended blocked, even if the event occurred, okay, some event it is waiting and it is occurred, then it is goes from suspended block to the suspended ready state. Okay, so now if you look at this part, this is a new part. This entire part is a new part, and this entire part is utilized by using your secondary storage if enough memory space is not there, right? Enough memory space is not there. So I hope I am clear with this concept of a process state transition diagram. Just recapping it, that we can have different system. We can have a uni-program system where a process will be keep on executing, and then we have a multi-programming system with non-preemption, and in that case it will be in this loop, but there will be multiple process will be available. Then the third dimension is preemption, and that is an external something that can take out the running process to a ready state. And finally we added the dimension of suspension if there is a lack of memory spaces available, right? So I hope I'm clear with all this concept, and you understand the entire process transition diagram. Thank you.